In this video, we're going to look at how to find different p-values using a standard normal table. So anytime you're working with a proportion, that's when you're going to want to use the standard normal table to find your p-values. So looking at this first example, notice we're trying to prove that the population proportion is less than 0.7, and we found a test statistic of negative 1.041. So what we first start by doing is drawing our standard normal distribution, which is centered at 0, and we're going to write down our test statistic. Now notice here, and actually I'm going to round that test statistic to just 2 decimal places, so we can ignore the 1 there. Now notice in the alternative hypothesis you've got a less than sign. You can think of that as an arrow pointing to the left, so you're in a left-tailed test. And so really what we're interested in is the area to the left of the test statistic. And this area here is equal to the p-value. So we can use the standard normal table to help us find this area, just like we did, back in Module 7 when we found the areas under curves. So we're going to go to our standard normal table. Let me erase this work. And so notice that we've got that z is equal to negative 1.04. Well, remember when we use a standard normal table, we look the left 2 numbers on the left column. And so that's right here. And then we've got the 4 from here at the top. And we see where those meet up, which is 14.92, and that tells us the area to the left of this point is 4.1492. So coming back here, this area is equal to 0.1492, so therefore the p-value is equal to 0.1492. Alright, now the next one down. Notice that in the alternative we've got a not equal to sign. Anytime you've got a not equal to sign, that means you have a two-tailed test. And we found a test statistic of 3.0371, and I'm actually going to round that to 2 decimal places. And the reason for that is when we look numbers up on that standard normal table, we can only look them up to 2 decimal places. So drawing a picture, our standard normal is always centered at 0. Our test statistic is 3.04, but we have a two-tailed test. So that means not only are we interested in the area to the right of this number, but using symmetry, we want to go to the left and use the negative 1, and we want the area to the left. So whatever number you have here in our two-tailed test, whatever your test statistic is, you're going to use symmetry and look at both the negative and the positive value in the area to each of them. Alright, now remember that our standard normal table will give us the area to the left of numbers. So we're going to look up this negative 3.04. So we're interested in negative 3.04. Well, so we come up here, negative 3, there's the 4, so 0.0012. So this area right here is 0.0012. Now, because this curve is symmetric, it ends up that the area is the same in both sides of the tails. So since the p-value is equal to that area, it's going to be equal to 0.0012, the area to the left, plus 0.0012, the area to the right, which is equal to 0.0024. Alright, our last example we've got here. Notice in the alternative we've got a greater than symbol. That looks like an arrow pointing to the right. This is a right-tailed test. So again, I'm going to draw my standard normal, 0, and my test statistic here is 4.02. So again, this area is the p-value. So I'm going to use my standard normal table to help me find that. So going over to my standard normal table, The z I'm interested is 4.02. Now, remember that the standard normal table is always going to give you the area to the left of the value. So when I look this value up, it's going to be giving me all of this area. So I'll have to do the 1 minus to find the area that I want. So these are all negative, so we're going to go to the next page. And again, just to help us remember. All right, now notice the largest value that's on this table is 3.409. Our z is so big it's not on this table, and that happens a lot. So notice here, when we have 3.49, so when z is equal to 3.49, if we drew our normal curve, this area here is equal to 0.998. So the area left in the tail, there should be a 9, 8, I missed a 9 there, is equal to 0.0002. Now, our test statistic, and again, this is if we had 3.49 here, our test statistic is even further out to the right, so it tells us that the area we want is even smaller than this value. So what we're going to say is, going back, since the smallest value we've got on this table is this, we know that our p-value is something less than 0.002. And again, that's because that is the smallest value that we could have found on the table, and we know ours is even further out, so we just say that it's very small. And this is generally how we'll say this. You'll see this written different ways. A lot of times places don't like to have the 2 here. They like to have it with a 1, so they'll say p-value less than 0.001. And notice this is still true, because we know if it's less than 0.0002, well, 0.001 is bigger than this number, so the p-value is still less than the bigger number. More commonly, you're going to see it written this way, just because people like to have the last number be a 1 when they're writing it as these inequalities. And again, notice I'm not saying it's equal to it. I'm just saying, hey, our test statistic wasn't even on our table, so we know our p-value is really tiny in this case.